Hi, Kostas. We'll be talking about embeddings today. And I have to warn you, this is not a Python talk. It's mostly maths. So if you want to leave, I can live with that. So, the discussion will be focusing around not only word2vec. Most of the people I know that are using embeddings are mostly using word2vec for some reason. Most probably because it's fast and it was the first one that was actually introduced some years back, 5-6 years back. So how many of you do you know word2vec? Cool. How many of you have trained a model yourself? Awesome. GloVe? Okay. fastText? StarSpace? word2vec? No. Okay. So you see the distribution of things, how it goes. Essentially, I'll show slides in a bit. Word embeddings are mappings from words to dimensional vectors. So say you have these actual numbers come from a GloVe model, the 200-dimensional GloVe model, and the word machine is mapped to this kind of vector, and the word intelligence to that vector. Why we're doing that, we'll be discussing that in a bit. And let's go. Here. What? Sorry. Oh, come on. Sorry. Because it's kind of not so convenient to write math on PowerPoint. Okay, cool. So we'll be doing an overview of word embedding models and their properties. We'll be discussing what are they, and why they are so important. There are several models in the literature. We have already mentioned the most common of them: word2vec with two variations, GloVe, fastText, StarSpace, word2vec, and there are even more Poincaré embeddings for hierarchical models, which I don't even touch. There are several ways and literature around that on how do we actually create embeddings for combination of objects. But let's get started. Why word embeddings? So, you most probably know that the typical text representation for words in documents is one hot encoding. So we have a huge vector with the dimensionality of our vocabulary, where everywhere 0, except the position of the word we have 1. This representation is very cool, but has also some issues around that. If we want to measure some sort of distance between words in the vocabulary, with one hot vocabulary, we'll be having the same distance between all words with any given distance measure or similarity measure. It would be very, very nice to have a property that will map distance of similar words in semantics very close in the d-dimensional space from a geometrical point of view. And third, we would like to have a compact representation, dimensionality, because if we have, say, a vocabulary fit in a model on Wikipedia or the web, we can have hundreds of millions of words, and that's not convenient for computational reasons. And ideally, there's a thing called word analogies. We would like to have as an output a representation that we can actually turn semantics into linear algebra. Right. So given the vector king, if we subtract the vector man and add the vector woman, we'll be getting something which is really, really close to the word queen. This comes from the word-vec paper back in 2013, and I think it's pretty much everywhere in every single NLP paper these days, or embeddings paper. All these concepts are coming around, like the theory behind all this work is what we call the distributional hypothesis, which origins back in 1954 by Harris. And it's a very reasonable one. Claims that the words that occur in similar contexts tend to have similar meanings, which is kind of obvious, but it's a very good place to start. And a more poetic statement, you shall know a word by the company it keeps, which is, again, it's a very nice one. I like that. So, we'll skip one. Okay, here comes maths. From the distributional hypothesis, we're jumping to probabilistic language, to statistical language models, because we're essentially trying to model the probability of a word that will appear after another word, in the sense of like the company of words, distributional setting. There are several methods to learn a statistical language model from raw text, but most of them, or actually all of them, have a common problem. There will be always sequences in natural language which you don't have in your training corpus. So you cannot assign probability 0 to a sequence, right? So if you have, like, for example, statistical language models are heavily used in voice recognition. What we'll be saying next heavily depends on what we have said already. But at some point, there can be sequences of words never uttered before or never appeared in our training corpus. And we cannot assign 0 probability. 0 probability will crash our models. We don't want that. So the core idea back in 2003 by Benjo, which is kind of like groundbreaking, is that can we use a neural net to approximate this probability distribution? So a statistical language model then is defined as the conditional probability of the next word given the previous ones. We're doing some simplification and disregard most of the words, and we're keeping a window of n words, the n-gram model. And then we use a neural net to approximate that model. And we're getting back in the hidden layers an approximation of what we call vocabularies over by the dimension of the hidden layer. First representation done. That was very interesting. It was a very interesting approach, but it was slow. Because the last layer of the neural net is a softmax over several million of words, and it's very slow to train. Sorry. Sorry. Okay, so you have. In theory, oh, okay, cool. I changed it to not to sleep, but that wasn't really theory. So softmax over several hundreds of millions of words, slow. First models taking like 2 or 3 days to train. Fast forward to 20 years later, 2013, Mikolov, all being at Google at the time, introduced word2vec, which essentially is just a disclaimer. All the models are not deep learning models. Especially word2vec is not a deep learning model. It's a shallow log linear model. So they're introducing word2vec with 2 variations. Cibot and Skiplegram will be discussing a little bit about that later. And they come with several hacks to improve performance. Negative sampling, hierarchical softmax, asynchronous stochastic gradient descent, modifications on the loss function, and so on and so forth. It trains really fast, like several hundred million machines, like less than half an hour, and can also exploit parallelism, can use all of the cores in your machine. Cool. And also comes with a nifty property, king minus man plus human equals queen. So yeah, people but really, really excited. Cibot, like I said, word2vec comes in two architectures. CBOW, which is essentially continuous bag of words. So in that context, we're trying to predict next word, like the neural net tries to predict next word given context. Right. So you have the context, every like a drawing on the left is essentially one hot decoding of each word that appears in the context, and we're trying to predict the word that follows, or the one set depending on your recording. And in the middle, the W matrix is essentially giving the embeddings matrix. It has the dimensions of a vocabulary by anywhere and the dimension we're after. The other way around, skipgram, we're trying to predict context given a word. Right, so we're like in a sentence, we're defining a context of, say, 5 words. We're somewhere in the middle, and we're trying to predict all the other words that most probably surround the word in that context. So no maths from that. Loss function is essentially cross entropy. So yeah, I won't spend too much time on that anyway. Okay, 1 year later, GloVe comes into play, which is a completely different approach. This is not like a probabilistic language model, neural language model approach, but it's rather a co-occurrence matrix approach. It's kind of like similar to LSA, latent semantic analysis. So what they do is, given a corpus, we build the co-occurrence matrix of a given window, context window, say 10 words or something, where most of the times the matrix is symmetric in the sense that the word I and the word J appear in the same context, so we don't do like something strange around that. And then we're defining a very weird objective function, which I'll explain in a bit. And by minimizing that function, we're getting back our representations, our word embeddings. This is essentially a least square regression problem. And we have the X. The X is the co-occurrence matrix, right? It's N by V by V, where V is the size of the vocabulary. We have 2 word vectors, and we'll discuss a little bit about that, like left and right context, for the word I and the word J, and every single pass on the matrix. There is a correction that follows. I mean, just a pause here. The word2vec paper was really, really hard to follow on the maths, and people spent like 2 or 3 years trying to decode why it was working. More or less, same holds with GloVe. It's much, much simpler, much more clear in the maths that implements. But there are some assumptions that are there to just make it work, and it doesn't feel completely right. I mean, word embeddings are working, but most of the people don't know why. There are some literature, and we'll be discussing that later. So Pennington and all are also including the bias words, like the bias terms in the objective function. And there is moving out frequent words with the function f, which is essentially suppressing stop words that appear too often on the training set. We're optimizing this function again with AdaGrad, asynchronous stochastic gradient descent, and eventually we're getting back the embeddings as like the sum of the 2 word vectors, I and J, like the left context and the right context. We do that because at some points it might be necessary, depending on the use case. We might end up with not having a symmetric co-occurrence matrix for some reason. And that will give us the ability to learn different representations. I mean, WAs and WJs, essentially, like left and right context, they're very, very close, and they're only different because random initialization is justified very well in the paper. And with some hyperparameters of like A and X max, which is essentially used to smooth the effect of very frequent words. Followed that, 2016, again, because of some other people from, which I can't remember the name, sorry, from Facebook this time, are using fastText, which is essentially an extension of word2vec, right? And the idea is to enrich embeddings with subword information. This is massively useful, for example, in scenarios where we have like spell errors, like in a search engine, for example. You will just get similar words really, really close in the embedding space because you're essentially looking on their n-grams, character level n-grams, and the hypothesis that because it's going to be like replacements or missing characters, their n-grams could be very, very similar. So essentially what they are doing is they're getting a word, splitting the word in n-grams, learn embeddings from the n-grams, and calculate the final embedding as the sum of all the n-grams, which is cool. And it works, like I said, it's the average of the n-gram embeddings. And works pretty well for cases we have like spelling errors or typos and stuff like that. Okay. Some months back, I think it was like end of 2017, another Facebook team came up with a generalization of embedding techniques, which is, they call it StarSpace. This one is not only for text. The Facebook page the Facebook GitHub page of StarSpace has examples of link prediction, graph inference, graph embeddings, and so on and so forth. And essentially, at any point in time, you can replace natural language processing with any system that has tokens. You can actually apply that on code. You can apply that on potentially music and so on and so forth. As long as you have data, you don't care what the vocabulary is. We're using, for example, in Argos, embedding techniques to learn similarity from clickstream. Where a document is essentially product codes viewed together in a session by a user. Say, for example, it works very, very well. So, StarSpace. StarSpace generalizes things a bit with an optimization objective which consists of two concrete parts. The loss function per bats, where the loss function can be either hints loss or softmax, and a similarity function which can be cosine similarity or just dot product. And we're learning representations over entities where we're defining the bats, like the loss function. We're giving it a positive example. So we're at the word x, and we're looking for the word x plus 1. So that can be like a positive example. And similar to word2vec and negative sampling, we're just generating a bunch of negative examples. Pause. Negative sampling. One of the ways to speed up the calculation of the output layer and softmax in being like millions or billions of words over vocabulary is to actually sample words from the vocabulary. So you know in advance which word is correct, and instead of doing softmax in the entire million words vector, you're just sampling a small number of them, say 10 or 50 or 100. That is an approximation, of course, but works really, really well. So this is like in the same case, in the same like mentality. We're generating positive examples and a bunch of negative examples. We're defining a loss function that actually quantifies that, turns that into a number, and we're trying to minimize the loss. Cool. Okay, bonus round. Round work. This is an awesome paper. These guys, this is our orator. These guys are doing some serious work around embeddings. So people were asking why this thing works, right? And there are several interesting questions to pose around that. Why essentially, what's the property of natural language or any co-occurrence model, like a distributional model that turns words, entities from distinct representations into continuous representations while maintaining their similarity, what we define as similarity anyway. That's a very good question. The second question is, empirically, it appears that most of the models in like mainstream NLP tasks are working better in moderate dimensions. So if you just train a model with dimensionality of, like, say, 500, will most of the time it will perform better compared to a model with 1,000 or even higher dimensions. So I think it seems there's a sweet spot between dimensionality and performance. And that's something that it's very, very interesting. So these guys are coming up with yet another embeddings model where they model, they approach the problem with a generative model, right? So what they say is okay, say, let's imagine that we have like a unit vector somewhere like in the vocabulary space, which points towards a direction. The direction is what is being discussed. It can be sports, it can be politics, and so on and so forth. Then, next word, like in the sequence of the word that is going to generate, is coming from like sampling the distribution of the dot, like the x value of the dot product between the discourse vector, like the random vector, over the vocabulary, right? So words that tend to be similar, in general, will have higher probability to be selected. For example, if you're talking about sports, say like football and so on and stuff, all these words are much more likely to be up to appear as next words rather than, I don't know, like neural nets. You most probably, it's not so typical to find neural nets or optimization functions in the sports article. Okay, and with some mumbo-jumbo maths, which I'm not sure I follow, they're ending up in two objective functions. The first one is essentially the frequency of, like, again, the cocurrence matrix, where essentially they're learning the vectors phi, u or v or whatever, with the first objective function, given some hyperparameters c and so on and so forth. And the second optimization function use pairwise mutual information, which is again closely related to how word2vec works, and that's yet another paper. So the pairwise mutual information is essentially the log of the probability of two words appearing together by their product, and so on and so forth. Okay, now, say we have the embedding model of our choice, and we want to build features for our machine learning algorithm. How do we do that? Most traditional machine learning algorithms are working on fixed dimensions like logistic regression, support vector machines, and so on and so forth. A cool observation that comes again back from word2vec is that in short contexts, of size, say, 5, just adding vectors together works very well. So, say, for example, you're trying to, you have like you want to build a classifier for metaphor detection. We'll be discussing that in a bit. What you can do is detect the verb in the sentence, get the context, left and right, 3 words on the left, 3 words on the right, get the representations, the embeddings, sum them up, and feed that as a positive or negative example in your model, right? That's one thing that works. It's like a naive sum or average of n words in a context. There are several other nifty approaches around that. I also discovered one just this morning. It was on a previous talk, again, coming from Facebook. It's to get, instead of get like the naive average of n words, get the average of the unit norm of the vectors that are composing the sentence. Essentially, the problem relates to how do we compute, how do we actually obtain sentence embeddings, right? And again, Aurora told the guys from Radwell come with very interesting approach. So say you have a document and you want to have document embeddings. You compute the embeddings by getting all the words that compose the document as a weighted sum of the probabilities in the corpus. Different words have different frequencies in the corpus. Formulate this matrix, take the first principal component, and you have your embeddings. And this works really, really well. It also follows the random walk approach, again, which is like a little bit heavy on math. Implementations. No, they're not to Python, sorry for the typo. The links for the implementations, word2vec is on Google site, GloVe comes from Stanford, fastText and StarSpace are coming from Facebook research. Broadwalk, there's no implementation yet, but we've been working on that, and most probably in the next following month there will be an implementation in Python for that as well. In Python, you most probably all know Jensen, which is an awesome tool for topic modeling and embeddings in general. It implements word2vec and also doc2vec, which is essentially an extension of word2vec, where along with the text, you're also including labels or metadata that surround it. So if you say, for example, you have I don't know, you have text and you have also labels like sentiment. You're learning sentiment representation or tag representation in general. It can be very, very useful in some cases. And also, there's a very, very nice implementation in GitHub from us in GloVe Python, which is essentially getting the implementation of GloVe and turned to Python-Cython implementation, which works really, really well. Now, applications in NLP. Metaphor detection. There is a paper following up on that. It will be actually presented at some point, like in the next couple of weeks, of some research we've been doing with some colleagues and friends down University of Athens. What we've been doing is label something like 2,000 sentences with some of them as metaphors, 50-50 like ratio, and the other literal. Train the model in a corpus of Greek text of something like 30 million words or something. Then we're locating the verb in the sentence. We're getting the context, left to right, get representations, and use that as features for our model. And that works with very, very high accuracy comparing to other approaches. I think we're approaching or something like 78% of accuracy, which is in metaphor detection something really hard. It's like a very, very good result. Same structure also on sarcasm detection. Sarcasm is yet more difficult than metaphor, so results are looking promising but not as good yet. And there is another approach from another work. Say, imagine you're in a newsroom and you're tagging, curating texts like articles, and you need to somehow rank or reject articles based on their propensity to be good or like high quality journalistic pieces. So get all the already approved articles along with all the rejected articles, get their document representations with any of the techniques discussed previously, feed that to a machine learning model, and get a probability of a new article to be good or likely to approved. So that's a very interesting, again, research in progress at the moment. There is. That sucks, so I'll change it. There's another yet application. Most probably, have you ever worked with recurrent, like sequence to sequence or RNN models? So, yeah. you know that there is an embedding layer. That one common way to do it is just let your model care as PyTorch to train it based on your corpus. But if you already have a pre-trained model or can get a pre-trained model, what you can do is, say, for example, download a GloVe model or a word2vec model, load the weights for all the words in your vocabulary, pass the weights in your embedding model, and prevent it from training, like make it not trainable. So that will be something like that. We have the embedding layer, and instead we're fixing the weights calculated, loaded from an pre-existing downloaded model. It's kind of like transfer learning, this scenario, and making it non-trainable. So the optimization process won't spend time trying to optimize the weights on that layer. And that's also very cool. If you have like complex sequence-to-sequence models, you can save lots of time. And especially if you have like a model trained on Wikipedia, most probably, whatever your model is, it won't be as good as a model you get from Wikipedia. And thanks very much. Questions?
Do you have any preferences to when you... So of the different embedding models you talked about, do you have any preference as to when you use which? Or are they just better? Good question. Are they just kind of better?
I think it's part of like of my grid search, which works best. For metaphor detection, word2vec seems to be working much, much better than GloVe, like in terms of like almost 15% higher in accuracy. I'm not sure why, right? There's work to be done there. For things like trying to find what the user means when they're doing search query, fastText is awesome, because essentially you can get similarities of like misspelled words, typos, and so on and so forth. And there's also a parameter of running time. So GloVe is much faster as long as you have the co-occurrence matrix. But co-occurrence matrix can take some time to build. But then on the other hand, you can just create it once with a specific cutoff window of word to be appearing at least 100 times in the corpus and so on and so forth, store it, and then iterate of many models on that, because essentially there are two separate processes. One to build the co-occurrence matrix, the other one is to train the model on the co-occurrence matrix.
Thank you. Any more questions?
Sorry.
To what extent do LSTM models fit into all the other models that you mentioned?
Sorry?
To what extent do LSTM models, long, short, term models, is that embedded in some of this information, or is that completely a separate model into itself?
If I get your questions right, it's like how the model performs with that, or how do we actually plug embeddings, pre-trained embeddings on LSTMs?
The first one, yeah.
How the model performs? Again, it's application dependent, I guess. So it's trial and error. It's like high non-linearities. So reasoning about why a model is better than the other, frankly, I don't know.
Thank you for the talk. Is in RandWalk the discourse vector C sort of similar to the center loss and something like? How do you initialize that discourse vector C?
You initialize it randomly, essentially. So at each point in time, you're pointing towards the direction. You're sampling words based on that direction, and then you're displacing the vector a little bit and carry on. And with some maths that follow, you can
so it's like a center point.
Yeah, it's kind of like a pointer pointing to what's being discussed, and then we'll follow up with the objective function, minimize that to get the embeddings. it's kind of like, I think it's round-walk and word2vec, I think, can be safely classified as energy models. Okay. Perfect. And then...
Just a bit of a technical question. So you mentioned 200 and 300 as embedding sizes that are reasonable for GloVe. For words, what happens with articles and embedding sentences and articles? Are they the same sort of embedding size?
My PhD is actually mining writing style, so it works amazingly well with the normed average, up to the point that if I have, say, a user with, say, less than roughly 500 tweets and split the tweets in two, what I'll be getting back is two vectors that are almost identical. So it seems to be work really well. It heavily depends on the style of the document, right? For different levels of complexity of vocabulary and so on and so forth, that heavily affects, of course, the output, because you're blending words in all possible ways. But style matters, like the style as in choices of the vocabulary as a generating text process. And please.
We have time for a few more questions.
Thanks. Thanks for the talk. Very interesting, by the way. You mentioned document embeddings. How do document representations compare in terms of performance and interpretability to something like topic modeling with LDA?
I haven't done the comparisons. For some problems where essentially we want to compare entities in general, where entities are essentially sets of words like sentences, documents, and so on and so forth. There are several techniques. Some of them work, like similar to the previous question, work really, really well on specific problems. Others don't work that well. For example, short sentence representations seem to be working really, really well on metaphor detection, because essentially we've done a statistical test. We just get like all the sentences we have tagged, metaphor and literal. There is a very interesting property. The average distance between verb and object in metaphors is much higher than the average distance in literal, as they are mapped in the embeddings model, which translate again to some various very interesting linguistics theories that as humans we're essentially, when we're doing metaphor, we're trying to localize to 3 dimensions metaphors. We're just like put in space and time, essentially.
Okay, so would something like rand walk work better for like a topic representation?
If you just wait like for a couple of months to have like an implementation, I'll let you know.
Okay, thanks.
Thanks.
Wow, that was a great talk. Great questions. Thank you, Kostas. Let's give a hand to Kostas.